joining us for this. I think this is the last video for chapter 9, the reactions of alcohols. Now, the last thing we want to tackle is synthesis, a couple of synthesis problems. And I just want to go over with you like how to think about that. For this kind of stuff, just keep in mind that the answers I'm writing out is not what's important. It's really how you think about it, right? Like how I'm coming up with the answer here. That's what's more important. So take notes on that as well, the thought process, not just the answers. Now, before you can tackle how to do the synthesis problem, often you kind of need to have a pretty good catalog of all the reactions we've learned in this chapter and the related chapter. I'd say also chapter 8. So for that reason, I would recommend that you might even pause this video and go do the work on the summary of all the alcohol reactions worksheet that I put on the canvas, which looks like this. Okay, and this is just an example. This is not quite comprehensive. You should put together like a summary notes that looks like this and fill in the blank. And then of course I trust you could fill these blanks based on the notes. And in fact, if you can't, it's a good idea to go back and study the notes again. Okay, but let's think about the synthesis problems here. Okay, now remember the retrosynthetic analysis idea. You should always start thinking about the synthesis backward from the target structure, not from the starting material, even though we're supposed to make these from this epoxide starting material. If you just start thinking only from this, it's a little bit harder. Okay, so yeah, and let's, before we begin looking at the nitty-gritty details, let's look at the sort of the big picture here, which is revealed by the stereochemistry, I would say. Compare this stereochemistry with that, as well as this. Do you notice that in the bottom structure, the stereochemistry is inverted? Right, the chirality is inverted, whereas here it's not inverted, it's really the same. And if it's hard for you to see that, you should build a model. Okay, now maybe we'll take a note about that. So this, so that means an SN2 reaction happened at this carbon at some point, right, to get to this structure. Okay, so that's a big clue. Now, this stereocenter is the same. Which means that SN2 reaction did not happen here. And even though I said don't start thinking from the starting material, it's an epoxide, so that means at some point the epoxide ring was opened. And when it did, in the top, to get to this top product, this product, SN2 or something like that might have happened at this carbon, but not at this carbon. For this product, SN2 happened at this carbon, but not at this carbon. So for the top here, SN2 type of opening happened at the less hindered carbon. At the bottom here, it happened at the more hindered carbon, which means some sort of acidic condition, a basic condition to open the ring. Hopefully that makes sense. If that doesn't make sense, you should go look through the notes from last time up there. Okay, now let's start thinking perhaps from the top, or maybe the bottom one is a little easier. So another thing you want to pay attention to is what functional groups you've got. You got ether, that's kind of new, and ester, of course, that's new. So one of the things you want to think about, do I know how to make those functional groups? Now, to make ether, those conditions are fairly harsh, like really strong nucleophiles, a base or really strong acids that could interfere with the other functional groups. So let's think about making the ester functional group last, which means that's the first thing we want to think about, right? We're thinking from the last step. So in the last step, we're saying we made a ester, and the only reaction we've learned in our class that makes an ester is from carboxylic acid. Do you remember what this is? Right, Fischer esterification reaction, which requires the alcohol and some catalytic amounts of strong acid like sulfuric acid or even tosic acid, toluene sulfonic acid. Okay, so that would do it. Okay, so now our task is to make this molecule. How do we make that? Right, let's look at some functional groups. Some of the new ones, of course, would be the carboxylic acid. Do we know how to make a carboxylic acid? Well, this isn't from chapter 9, but last chapter we learned about oxidation of alcohols, right? So we should know how to. By the way, this phenyl group, this is called a phenyl group. It's a benzene ring, but when it's attached to something else as a functional substituent, it's often called a phenyl group. Abbreviation for these three double bonds, when it comes to just the phenyl group, you could do this, okay? Remember that you could oxidize a primary alcohol all the way to carboxylic acid using harsh oxidizing agent. And do you remember what that is? I can't remember if we named it, but it's also called Jones reagent, and that would work, or sodium dichromate and sulfuric acid and water. Right, that would work. That becomes chromic acid in situ, and that's the oxidation. So now the question is, we have to somehow make this. And this awfully looks like, remember, there's an SN2 happen here to open the epoxide, and when the epoxide opens, of course, we get alcohol, right? That was the case like this. Something adds, opens alcohol. And remember, we want the opening regiochemistry to happen at the more substituted carbon, where there would be more partial positive, which means we want this to happen under acidic condition, right? So what would be a good example? Perhaps we could use, again, sulfuric acid to make it acidified. What is the species that attacked at this carbon to confer that inverted methoxy ether? Well, it would be alcohol that looks like this with one carbon, so it must be the methanol. Okay, to do that. And now for sort of review of everything, it would be a good idea for you to think about the step-by-step mechanism for each of these three steps. But we came up with a three-step synthesis to this molecule from that epoxide. Okay, let's think about this other one. Now, this time we're not thinking about the inversion here, but let's think about the functional groups that are present. We could either make this ester, that could be the last thing we make, perhaps, or we could make this ether. Now, earlier we said that ester is probably a better functional group to make last because it's a little bit more labile, but in this case, perhaps let's think about maybe making the ether last, okay? And part of the reason, though, is, well, if we were to make the ester last, what would happen? Is we would have to make this ether. Now, when you make this ether, assuming we're going to do Williamson ether synthesis, we would have to turn this into a good nucleophile and then react it with methyl bromide or something like that to make this bond through SN2 reaction. When that happens, likely this oxygen would become alkoxide and act as a better nucleophile than that tertiary, more hindered oxygen. So the methyl ether would form over here before it ever would form over here. Now that would be the problem here, okay? And so for that reason, I'm going to, I guess I can leave it there for now. I'm going to make this ester first. That means we're going to make this ether last, okay? So that's the first step we're going to think about because that's the last step. Okay, so how do we do this? So what we're saying is we're going to make this ether, methyl ether from this tertiary alcohol. Okay. Using a Williamson ether synthesis. First step, we need to remove that alcohol proton. We need a good base like that, a strong base like that. And then we would need something like a methyl with a good leaving group, say iodide, right? And that would do it. Now, if you're worried about any of this reacting with the ester here, which it could, but what we are generating in this tertiary alkoxide, which is again very hindered, so it likely won't react with these other functional groups, but it could react with a tiny substrate like methyl iodide, and so that's the idea for the synthesis here. Okay, so now that our task is to either make this alcohol or this ester, perhaps we'll think about making the ester functional group. So at this point, I guess this is kind of irrelevant, so I'll delete that. So before we make that ester, the structure must have looked like, remember ester is made from alcohol and carboxylic acid, and that would be the precursor. Now, there's one thing kind of bad about this precursor because there's two functional groups that are the same, both alcohols. It's good to be able to distinguish two functional groups, both of these oxygens. So it's kind of a disadvantage when both of them are the exact same functional groups. Here, there are two different functional groups, alcohol, ester, so you can distinguish the two so that you could do different synthetic maneuvering to the two oxygens. So that was nice. Now they're the same. However, one's primary, one's tertiary, so they would have very different reactivity. So hopefully this is still fine. Okay. So now, how do we make the ester? Well, the only reaction we know is Fischer esterification. So we could propose this carboxylic acid and reacting with this alcohol. Now, how do we know it would react with this before that one? Likely because this is the less hindered nucleophile, which makes it a better nucleophile. Okay, so now our job is just to make this, which really is the open version of this epoxide. And remember, we said that there's no inversion here, but perhaps there's a SN2 attack on this carbon. So how do we do that? This would be the nucleophile that would have opened it. So we need a hydroxide, right? Okay. So that should complete the synthesis.